Okay, we consider something like this. Let's consider delta z. Okay, delta z will be, of course, the difference between, let's say, z minus z sub 0 or z minus c, if we are looking at the point A, B, C. Delta z will be defined as a plus delta x, f of a plus delta x, b plus delta y, minus the actual value at a and b, f of a, b. That's what that's a definition of delta z. What we'll be interested in when we talk later on, the next topic after differentiability is differentials. To take that delta z, make it dz, make it the complete differential. Remember, notice that there is a parallel between what we're doing here and what we did in Calculus 1 when we learned that in, I believe, chapter 3, section 10. We learned about the linear approximation, and then we talked about differentiability, and then we talked about differentials and how to use those. Same here, the same structure. So let's just write that where delta x in this case is x minus a, and delta y is y minus b. Okay, so here comes a definition for differentiability. We're going to say that suppose the surface S is the function z of x and y, f of x, y, then f is said to be differentiable at AB if the following happen. Delta z is del f del x at AB times delta x plus del f del y at AB times delta y. Okay? So, remember, delta x and delta y are defined here, but we have an error. This is an approximation. So, in order to make up for the equal sign, we need to include two error components. So, epsilon 1 will be multiplied by delta x, so x minus a, and epsilon 2 will be multiplied by delta y. This is not the same epsilon we use for the precise definition delta epsilon. In this case, epsilon 1 is the error and that introduced is caused by delta x, and epsilon 2 is the error caused by delta y. But in order to complete the definition, we need to include the following condition. Epsilon 1 will go to approaches 0 as delta x approaches 0 or x approaches a, and epsilon 2 approaches 0 as delta y approaches 0 or y approaches b. Okay, and Jake, I saw your hand, but let me make a couple of comments here. All right, so this is the definition, and we have a couple of comments here. One, first, we're going to say that if f of xy is differentiable at AB, then the linearization or the linear approximation near in AB is good. That's one comment. And the next comment is the following, and this is something that already we alluded to that. We're going to say that the tangent plane, and that's what started it all, the tangent plane is approximates the value of z. Man, some demands. The value of z on surface S near AB. All right, now I'll pause here, take your questions. Jake, I saw your hand coming up.
Back to when you go to differentiability, it's just that minus sign should not get equal sign.
Delta Z here equals up.
The third line down to that.
1, 2, 3. Huh?
You got delta or after.
That's minus. It's this minus that give you the delta. Z at AB is f of AB, but now what you do, you change a little bit, you move, and you take the difference.
Yeah. It doesn't, you have delta x being x minus a. So
No, it's...
So if you put that delta x in there, wouldn't it just be x after x and 1?
Yeah, it will.
Okay.
It would. Yeah, x is a little bit off A, and y is a little bit off B. So you're absolutely correct.